So folks, in the last video, we took the known function f of x was equal to sine of x, and then we looked at the new function g of x was equal to the sine of x plus 3. And usually that's clear from context. I'll go ahead and put parentheses around that. Now we're going to look at the function, it looks like I've labeled it k of x, is equal to 3 sine of x. And I want to point out the distinction between here, I've got the sine of x and I'm adding 3. And that gave us a vertical shift. In this problem, I'm multiplying by 3. And that's going to give the effect of a vertical stretch. And that's not a, there's nothing magical about that. Notice we did this before. If we were to plug in pi over 2 into our sine function, we would get the sine of pi over 2, and we can go obtain that value from the unit circle or one of many other ways, and we would get 1. So now if I were to do k of pi over 2, we would get the sine of pi over, 3 times the sine of pi over 2, which would be 3 times 1. And there's where I'm saying this is going to multiply the output of the function. It was originally 1, and now we're going to multiply that by a factor of 3. And that gives the effect of vertically stretching the graph of this function. So what I'd like to do here is let's sketch both these functions on the same axes. It's really kind of beautiful to see the vertical stretches overlaid on top of the original function here. So that's what I'm going to do. Let's do the x tick here. Let's go ahead and do pi over, we'll go ahead and do pi over 4 for that. And then for the y tick, again, because I have sort of limited room, I'm sketching both of these. If I were just sketching sine of x, I might let each y tick be half a unit or a third of a unit or something like that, just so that I fill up a little bit more of the graph. But here I'll let the y tick be 1 unit. So we know that the sine of 0 is 0, and we could plot the sine of pi over 4. I'm going to go ahead and skip that. If we were to plug in pi over 2, the sine of pi over 2 is 1. And if we were to step over 2 units, the sine of pi is 0, and the sine of 3 pi over 2 is negative 1. And this is the same graph that we sketched in the first video when we were looking at the graph of the sine of x here. So that graph should look the same. Okay, I'm going to clean that up just a second. And remember, folks, I want you not just to sketch one period of this graph or one portion of this. I want you to, whatever you choose as your scale is fine, but I want you to fill out the graph that I've given you, the coordinate system I've given you. So don't just draw the portion of the sine graph that's to the right of x equals 0. Sketch more of that. So let me put that on here. Okay. And just to plot a point there to make sure that makes sense, that was the order pair pi comma 0. And let me label this right here as the order pair pi over 2 comma 1. So I've got a couple order pairs plotted on there. I've asked you, to usually list several of these zeros. So let's go ahead and plot this one. This is minus pi comma, just minus pi comma 0. And this is just rehashing. We're just resketching the graph of the sine function. We know it well enough. We could probably sketch it in our sleep. But there it is. Okay, so now we want to look at the graph of k of x, which is, so there's the sine of x, there's the sine of x again, but now we're multiplying the output by a factor of 3. When I say output, I mean after we evaluate what the sine of x is. For example, if x were pi over 2, after we evaluate the sine of pi over 2, we multiply that by a factor of 3. So notice that when I plug in k of 0, somewhat interesting here, we'll have 3 times the sine of 0, but the sine of 0 is 0. And so just like f, k will output the order pair 0, 0 there. But when I input pi over 2, we saw that that would output a 3. So that would be this point right here. And these are the points we end up minus 1, 2, 3. We end up plotting for the graph of k of x. So I think it's really helpful to see that every single one of these outputs And although I didn't sketch this, this is pi over 4 right here, so that would be root 2 over 2. And it's not a perfect sketch, but it's about right there. But I'm going to triple that output when I go to get my y output over here, so that would be something, I don't know, maybe right about there or so. Okay. So let's go ahead now and finish sketching the graph of k of x. And here, you know, this is in some ways even better than some of the, you should have seen this vertical stretching technique in your college algebra classes. Let me sketch that just a little better. In your college algebra classes. But I actually think there's a lot to be learned when you look at these trig functions and you think about this idea of vertically stretching all of the outputs by a factor of 3. Notice at points that were on the origin, when I triple their output, I'm just tripling 0 and it remains at 0. But all of the other outputs that are non-zero, their y outputs get tripled in this process. Okay. So what I'd like you to do is I would like you to go ahead and sketch the graph of k of x equals 1/2 cosine of x. I'm going to help you out a little bit with the scale because you can kind of get into trouble with these. I'm going to let each x tick mark, just as before, be pi over 4. But I'm going to let each y tick mark, I'm going to go ahead and let each y tick mark actually be 1/4 just to accentuate things a little bit here. So when I go to sketch, I'm going to sketch this one with you. We know that the cosine of 0 is 1, and if I'm letting each y tick mark be 1/4, there's 1/4, 1/2, 3/4, 1. So there's the ordered pair right there. There's the ordered pair 0, 1. And if I'm letting each tick mark be a pi over 4, there's 1 pi over 4 pi over 2, but we know that the cosine of pi over 2 is 0. And then there's another 3 pi over 4, there's pi, and we know that the cosine of pi should be -1, but on my axes here I'm letting each tick mark be -1/4, minus 1/4, minus 1/2, minus 3/4, minus 1. And so there's the ordered pair. Let me scroll down just a little bit. Here's the ordered pair pi, -1. And once you've got a period sketched, you can kind of just copy. Notice I'm just sort of copying the every 2 I go over, I either go up 4 or down 4. So I'm going to go to the right 2 and then go up 1, 2, 3, 4. There's another point on this graph. And that enables me to start sketching. And it's not perfect, and you don't need to worry about being perfect here, folks. But just make sure you pass through the points you're saying you're going to pass through. And you can finish sketching out. Now, careful here, folks. Don't let the above graph deceive you. This is the graph of just, I think I'm calling this h of x. Yes, h of x is equal to the cosine of x. So what I would like you to try to do is I want you to try to sketch the graph of k of x equals 1/2 the cosine of x. And my hint to you is this. When we multiplied by a number larger than 1, that had the effect of stretching this graph out. Here in the absolute value sense, I'm multiplying cosine of x by 1/2. That's a number smaller than 1. That's going to have a vertical stretch or shrinking element to it. And in this case, it should be vertically shrinking each factor. So for example, and this is the last part I'll do for you, let me color code that. We had h of 0 was equal to the cosine of 0, which is equal to 1. Now we're going to have k of 0 is equal to 1/2 the cosine of 0, which is equal to 1/2 times 1, or 1/2. So I'll go ahead and plot that ordered pair right there. There's the ordered pair 0, 1/2. And I'll let you finish sketching this graph out, giving you the hint that it's going to be the original graph shrunk on the vertical axis by a factor of 1/2. So pause the video and give that a shot. Okay, folks. So just to summarize what we just saw here, If I were to take the graph of some known function f of x and I were to create a new function called g of x, and I'm going to obtain that by multiplying f of x by a value of a, this is just the graph of f vertically stretched by a factor of a units. If a is less than 1, then rather than saying vertically stretched, you're fine to say that it's vertically shrunk by a factor of 1 over a. Okay. For trig functions, like the for trig functions sine of x and cosine of x specifically, here we can think of a as measuring the distance between the min line and max-min values of the function. So if you go look at this graph right here that we sketched together, the understood coefficient in front of sine here is 1. And if you look at the difference between the midline, which for both of these graphs, no shifting was done to the midline. Here's the midline at y equals 0. For both of these graphs, the midline's at y equals 0. And for the first one we sketched, notice that the distance between the midline and this peak, or the distance between this midline and the valley, is the absolute value of a, which is 1. Or for the blue graph, the second one we sketched, if you look at the distance between the midline here at y equals 0 along the x-axis, and you count up, we're up 1, 2, 3, or we're down 1, 2, 3. That up or down by a factor of 3 is what we see right here. And we give this a term with sine and cosine. This doesn't work for tangent or cotangent, and it's not usually applied for secant or cosecant, although maybe you could do something like that. But we go ahead and call a the amplitude of the function. So for example, if I give you p of x is equal to 4 cosine of x, this has amplitude 4, whereas if I gave you q of x was 1/3 cosine of x, the amplitude would be 1/3. And that word amplitude refers to the distance between the midline and the peak, or the midline and the trough in terms of vertical distance. Okay, folks, that's all I've got for this video. I'll see you in the last part in just a moment.